Okay, so moving on now, we will introduce another conservation concept called the conservation of mass. Just as energy is conserved, a fundamental classical physics concept is the law of conservation of mass. So most situations, or maybe all, or I mean, we can say that all situations that we'll be dealing in this course will be where the mass is conserved. So, for example, we have here a substance undergoing heating process. So, say let's have a 1 liter of initially we have a 1 liter of water here inside a container, but after heating process, after the energy goes into the system, then let's say it reduced because it changed phase. So some of the mass actually goes out from the system. So say what's left is 0.8 liters. So where did the zero point 0.2 liters go? So if we have quantified that, let's say what's left is 0.8 liters, then that means that um, zero point 0.2 liters has been converted into vapor phase, right? So if you sum this up, the point 0.2 and the point 0.8 is still will be sum up into 1 liter. So that's what this conservation concept means, or conservation of mass means. So um, we're not just looking into the system, but rather we're also taking into account what's going in or what's going out from the system. So in totality, it must be conserved. So that means that mass is not destroyed, mass is not created, or mass is not destroyed. For some systems involving combustion, change of elements here. So when you say combustion, actually you need fuel, you need air, and then you need to bring those two together. Actually, air or oxidizer, any oxidizer. So air and fuel, and if you add heat, and the reason for adding heat is actually to bring the fuel to its ignition temperature. So once it's ignited, then there's gonna be release of heat. So that's combustion. Then and then after reactions, there's gonna be products, mass products of combustion, like the CO2 and other gases, combustible combustion gas or exhaust gas. So there's this mass of exhaust gas as well. Okay, so even if that's the case, then we still it is still in the domain of this conservation of mass. So still mass is conserved. If we track those, I mean, maybe if we track everything here, we still be able to use this conservation of mass concept. But for um, for some situations wherein mass is at the speed of light, so if mass is moving at the speed of light, let's say we have some elements here, or particles here, then it says mass is changed to energy. So maybe in nuclear fissions, or when a mass travels at the speed of light, so there is no more conservation of mass, because after that process, those masses are changed to energy. So this is actually expressed in the equation of Einstein, is equal to mc squared. So which means that if a mass travels at the speed of light, or squared of the speed of light, so this is really really fast, then that means that the mass is converted into energy. So in this domain, or in these situations, then we are not able, or will not be able to use these conservation of mass concepts, right? So I'm not saying that that in all situation mass is conserved. What I'm just saying, that for most engineering situations, is that we can apply this conservation of mass with satisfaction. I mean, we can get satisfactory results. Okay, so that's the concept. So now let's move on to the equations. So just like the energy, that it has this equation, so as this mass. So actually it looks the same, because what goes in, the sum of what goes in you minus the masses that goes out is equal to the rate of change of the mass in the system. So, so for example, we have a container here of water, and then we have two inlets or two sources of water that goes into the container. So let's say we have A and B. So therefore, there's a mass flow rate at A. There's a mass flow rate at B. Then we have three outlets. So mass going out from C, mass going out from D, and mass going out from E. So if we sum this up, so summation of in minus the summation of what's going out is just equal to the rate of change of the mass in the system. So there's this special case, as we have already mentioned when we discussed the conservation of energy, that we have this term steady state condition. And recall that when I say steady state, that means that there is no change, right? So steady state means properties do not change with time. Properties do not change with time. Right, so what property? So in this concept, conservation of mass, of course, we are referring to mass. So mass in the system, or the change, again, it's not that there is no mass in the system, but rather there is no change in mass in the system. So the level of water here, it will not go up, or it will not go down, or there's no change at all. If you have same amount of what's going in, the same amount of what's going out, right? So for steady state, then the right side is equal to 0. So that means that summation of mass going in is equal to summation of mass going out. So the left side is what's going in, the right side is what's going out, right? So that's just it. And then another concept, so mass flow rate. So the term mass flow rate, from the word flow, that means the substance is still flowing, and usually we are referring to fluids, whether liquids or gases, vapors. Let's just say fluids for now, right? So fluids. Okay, and flow rate, and when I say rate, we are talking about a time rate of change. So per unit time. Okay, so per unit time. That's right here, per unit time. So when I say mass, that means it's a mass per unit time. And what unit will you expect? That is kilograms per second. So the mass per unit time. Right, so if there's a moving fluid in a conduit, or whether it goes into the system or leaves the system. So if there's a conduit, or if there's a hole or a passageway, then we can actually compute the mass flow rate. Alright, so the mass flow rate is given by this expression. So recall that mass flow rate is in kilograms per second. So it's equal to the density of the fluid, the cross-sectional area, density of the fluid, and then cross-sectional area. So what area? So if we take a cross-section here, or a section cut here, so we are referring to this area. So cross-sectional area and the velocity. This is velocity of the fluid. So if you take if you do unit analysis, the density is kilogram per cubic meter. This one is meter squared, and velocity is meters per second. All right, so meter squared times meter, that's cubic meter. So this cancels out. So what's left is kilogram per second. Right, so that's just the basic equation for this mass flow rate, or fundamental equation rather. And when I say velocity, so when there's a moving fluid here, and there are fluid layers wherein it's near the solid boundaries or near the walls of the conduit, and that means there is this friction, and the velocity of the fluid adjacent to this wall will be, or will have a slower velocity than those fluid layer at the center, because right here there's not much friction here as compared to fluid layer adjacent to the wall, because we have this solid boundaries. So because of that, there is a change in, or that's the reason why we have this velocity profile graph. So let's say here along the vertical is the height, or the diameter, or the length, or the vertical length, and then at the x-axis, let's say this is the velocity. So that means at this point we have a zero velocity, but here we have a higher velocity. So that means that the greatest velocity occurs at the center line. However, for computation purposes, usually we assume an average velocity. So we assume a value somewhere right here. So that is gonna be an average velocity, right? Okay, so another one is the density. So the density of a fluid is there is data for this, right? So there is data, and if you take a constant value, then that means we are referring to some density value at standard conditions. But if not, then you can maybe expect some variable value of this density. Let's say if it's a function of time, sorry, function of temperature, or maybe function of pressure, right? And there's this relationship of density and the specific volume. All right, so recall that density is specific density is cubic meter per kilogram, so that's the opposite, or that's the reciprocal. Okay, another concept is this volumetric flow rate. So from the word volume, that means it will be in cubic meter per second. So it's a volume unit here in the numerator per unit time. So that's the volumetric flow rate. Right, so now I think we're done with the concepts, and we're now moving on to the sample problems regarding the conservation of mass. So first one is from one of our reference texts. It says here, water has an average velocity of 8 meters per second through the pipe. Determine the volumetric flow rate and mass flow rate, or mass flow, or volumetric flow. So we have a pipe, we have a conduit here, and we have a flowing substance, water. And what's given to us is the velocity of the water. So they have measured that it's 8 meters per second. The diameter of the conduit, or the pipe, is 300 millimeters in diameter. So what's the volumetric flow and what's the mass flow? Right, so that's straightforward. So maybe now we can just write solving for the mass flow rate. Right? So solve for the mass flow rate. Mass flow rate. Alright, so what's the equation? It's m dot is equal to rho times the cross-sectional area times the velocity. So the rho of water can be, right, so from table, or typical. Alright, so from table, right, so whichever table you have got this data, let's say from table something, the density of water at typical temperatures, temperature is 1000 kilograms per cubic meter. So it's a constant value, and actually we say that that water is incompressible. So that means usually there's no change in this density. Right, so 1000 kilogram per cubic meter. So next is the substitute. So m dot is equal to 1000 kilogram per cubic meter, and then the cross-sectional area. So what's given to us is the diameter, but we know that diameter and area is related by, so area is pi d squared, so pi times the diameter, but the diameter here is in millimeter, so we have to convert that to meter. 0.3 meter squared per divided by 4, so pi d squared all over 4 times the velocity of 8 meters per second, right? So meter squared, meter, cubic meter, so what's left is kilogram per second. So if you do the math, what you get here is 565 kilograms per second. So that's the mass flow rate. Okay, so next is, what's next? Let's solve for the volumetric flow rate. Alright, so number 2 is solving now for the volumetric flow rate. Okay, flow rate. So we can use, I think we can just use our equation, area times the velocity. So times velocity. So area is pi d squared, right? D squared all over 4 times this velocity. So if you substitute the value, what you get here is 0.565 cubic meters per second. And also, since volume and mass is related by density, I think you can also use that. So since density is mass per unit volume, so this is per unit time, this must be per unit time. So volume is equal to mass. Sorry, yes, that's correct. Mass divided by the density. So this can also, or this will also arrive to this value here, results. So it's the same thing, I guess. Right, so that's the mass flow rate and the volumetric flow rate. So now let's add some more sample problems. So it says here, a steady state steady flow device receives steam at a pressure of 500 kilopascals, temperature of 200 C, and a velocity of 30 meters per second through a circular inlet with a diameter of 0.05 meters. Steam exits the device at 200 kPa, 150 cm. I think 150 C is the temperature through an outlet with a cross-sectional area of 0.015 meters squared. Determine the exit velocity of the steam. So we'll be using the conservation of mass here. What's given to us, or here's the device. We have I think this is a diffuser, so a smaller cross-sectional area at the inlet, and right here we have a larger cross-sectional area. So which means if there's a large cross-sectional area, the velocity has to decrease. So we should expect a lower velocity here at v2, I think. Right? Because from the equation, Q is equal to AV. In order for Q to remain the same, that means that A and V is inversely proportional to each other. So Q over V is equal to A. So if this is constant, that means if area increases, velocity decreases. If velocity decreases, area will decrease. So they are inversely, area is inversely proportional to the velocity. So that's why here we have a maybe we can say something like a jet here, jet velocity. So if we have a smaller area, we can achieve this jet situation. So area is inversely proportional, 1 over. Right, so let me write again. Area is inversely proportional to the velocity. Take note, this is velocity, this is not volume. Right, so what's given to us are the properties at state 1 and state 2, so inlet and outlet. So I think this is not state, this is just simply yes, I think this is state because we have P1 and T1 right here. So we have a conditions here, we have also a condition. So it's the same with inlet and outlet. Right, so at inlet, so point 1 T1 and the velocity as well as the specific volume. So actually in the textbook, this one is not given, so you still have to find this specific velocity at the tables. But since what we are interested here is the conservation of mass, then I just included it here. So V1 is already given, the specific volume, because we need this because we'll be needing the density, right? So right here at outlet point, we also have a value of this specific velocity, the area. Actually, that's just what we need: the area, the velocity. This one is I think there's also another one given. So at the inlet we have d1. So let's add here, d1 is equal to 0.05 meters, 0.05 meters. Right, so I think we are good to go. Then we can solve for. All right, so let's try. So solve now. Alright, so conservation of mass. So applying, since everything is given, let's write here. Since everything is given, we can now apply the conservation concept, conservation of mass principle. So which means that the since did it say steady state, so let's add here. So assume steady state, right? So steady state, right? So right, so summation of mass that goes in minus summation of mass that goes out is equal to the rate of change of mass in the system, delta T. This is 0, so that means that the summation of mass going in is equal to the summation of mass that goes out. Right, or in simple equation, we can just write M in is equal to M out. Right, so what is mass flow rate? Isn't it the density here? Density times area times velocity, of course, at point 1 or at inlet. And here we have a raw AV as well, but this one for outlet. Right, so if we check for the inlet, what's given to us is the diameter. We have the diameter, and what else? We have the velocity, and we also have the area. So we can solve for this, right? At the outlet point, we have density, we have area, but velocity we don't have. Right, so that's why we first need to solve for the mass flow rate here, and then substitute this mass flow rate here to solve for the velocity. Right, so at inlet, the mass flow rate is so m dot in is equal to raw AV, but we don't have this density. What we have is the specific volume. So recall that density is inversely proportional to the specific volume. So that means area times velocity divided by the specific volume. So what's the area? It's pi d squared, 0.05 squared, pi d squared all over 4 times, right? So times the velocity of 30 meters per second, and divided by the specific volume of 0.4 cubic meter per kilogram. Right, so if you do the math here, what you'll get is 0.1386 kilogram per second. Right, so that's the mass flow rate. Okay, so what's next is, now that we have the mass at the inlet, and since mass at the inlet is equal to the mass at the outlet, then we can solve for. So we can now solve for the velocity at the outlet. Right, so what's the equation? So the equation once again is so m dot is equal to rho av, but we are solving for v, so that means m dot is equal to rho times a is equal to v. Of course, this is at point 2, or the outlet point. And what is 1 over rho? That's the specific volume. So we can also write that the velocity is equal to the specific volume times the mass flow rate divided by the area. Right, so substitute the values. The volumetric flow, specific volume is 0.95986, that's cubic meter per kilogram, times the mass flow rate of 0.1386, right, all over the area. So the area is already given at 0.2. It says here 0.015. So it's not diameter anymore. So 0.015 meters squared. And if you do the math, what you get is 8.87 meters per second. Right, so that's it. That's how we get the answer. So again, this problem, it gives us this pressure and temperature actually, and if this is not given, then you have to find this. So where will you find this? So through the property tables or charts, or any values where it is available. So it's not constant, because this is, it's not the 1000 kilogram per cubic meter, because this is a compressible substance. It's a steam, and it's a compressible substance. So it varies. When I say compressible, that means pressure affects the density. So that's the reason why you have to go into the tables to find this one. So the reason why I just give this straight to you is because we just want to be familiar with how to use this conservation of mass. Right, so last problem, I guess, is this one. So it says here, consider the device shown. The device contains 3 inlets and 2 outlets. Determine the time rate of change of the mass of water in the system at this instant. So we have a system that has 3 outlets, 2 kilograms, 3 kilograms per second, 5 kilograms per second, and what's leaving is 7 and 6 kilograms per second. So we are asked to find the rate of change of mass in the system. So inside here, is there accumulation? Is there a reduction of mass, or is it a steady state? So we have to find this out, right? So for the solution, then first is apply the mass balance equations, or mass balance equation. So summation of the mass going in minus the summation of the mass going out is equal to the rate of change of mass in the system. Right, so rate of change of mass in the system, we can write delta T per delta T, or we can also write just a dot above the mass. Right, so what goes in are the 2 plus 3 plus 5. Right, so let's write here 2 plus 3 plus 5. So those are the mass that goes in minus the mass that goes out, or 7 plus 6. So 7 plus 6 is equal to the rate of change of mass in the system. So if we do the computations here, what we get is a change in the mass of the system is equal to, so 2 plus 3, this is 5 plus 5, so 10 minus 13. So this is 10 minus 13, which is equal to 3. Actually, minus, so minus 3 kilogram per second. So that means there is a reduction of mass in the system of minus 3 kilograms per second at this instant. Take note, at this instant. So when say instant of time, it's like there's a flowing of mass of water, and then it can be changing. It cannot or not be changing, and then you take a picture of one instant. So at that instant, these are the values of the mass. Right, so it says here negative 3. So therefore, this is not a steady state system, right? So I think that's all for this conservation of mass topic. So next week we'll be doing some more energy analysis. We are going to apply simultaneously maybe the mass, the conservation of mass, and the conservation of energy, and all the concepts and principles that we have learned from topic, maybe topic 2 to topic 6. Right, so we are going to analyze some more devices for closed systems and for open systems. Right, so see you in the next video.